Hi, Simon.
Okay, so yeah, welcome everyone to this week's One World Machine Learning Seminar. And this week we have Eldad Haber with us from the University of British Columbia. Apologies that my video is not working. It's a technical mistake, not that I'm trying to hide. So it's a great pleasure to have Eldad share with us recent work on graph neural networks motivated by PDEs. And Eldad, well, before I give you the floor, just a quick comment on questions. If you have questions, Eldad said he's happy to be interrupted, so feel free to just ask your question if you have one. You can also put your question in the chat, and then I will interrupt Eldad for you at a convenient time. So with that, Eldad, you have the screen.
Okay, thank you very much, and thank you very much for inviting me here to talk on these things. This is work that we have been doing for, I guess, more than 6 or 8 months now, no more than that, on a graph neural network, which we started really looking at it from a context on other things, and then kind of came to this. My collaborators on these things are Moshe Yasuf and Eran Treister, both of them at Ben-Gurion University in Israel, and really the guy who's done a lot of the work, and I have to attribute is Moshe, who's run all the numerical experiments almost. So just to let you know that there are people that really worked really hard for this. I'm the one who probably worked the least hard on this. In terms of content, what we're going to talk about, we're going to talk a little bit about graphs. This is not going to be in any way a good introduction to graph, but it's just kind of what we need to get from the graphs. I'll talk a little bit about neural networks to try to kind of put you into the phase of what neural networks are and how we view them, or deep neural networks really, more than anything else. And I guess that by now people have seen the analogy between deep neural networks and ordinary differential equations, and then partial differential equations. And then I'm going to try to move to neural networks over graphs, talk a little bit about graph smoothing, which is what kind of started us to look at this problem really, and to see why people are not using the techniques which seems to us obvious somehow, and then talk about graph networks, graph operations, how you build a neural network over graphs, and really do it through something which I've not seen really, that talk about energy. So we're looking at it more from a variational approach. For mathematicians, that's kind of nice. This is a nice way to think about how to build neural networks. And that's a little bit different. Talk a little bit about specifically about the networks we're running, talk about applications, conclusions. And again, I'm trying to make this talk more tutorial rather than just throw names on this. So I'm not really mentioning any citation during the talk itself. So if you feel that you're insulted by this, you can send me an angry email after that you say that I should have been citing your work. I will completely agree with you. So again, let's talk for a second a little bit about graphs, or the way we look at what we need here from graphs. So you can think about graphs as a collection of nodes and vertices. That's really the way we kind of want to think about this. What we have, I don't know why there is the recording thing is just on my other screen. That's the only thing. So the graphs we're considering are going to be undirected. So we're not really thinking that if there is a connection between nodes, the connection goes in both directions. We don't really think about anything else. We think about the nodes as being where features may lie. So you can describe some things that happen on the nodes. Sometimes you have features on the edges, and then you have information that flows, if you want to think about it, between nodes through the edges of the graph. Okay. The way that, because I'm not originally a graph person, I'm a sparse matrix person, I always think about graph as a sparse matrix. It really helps me, but some people really prefer the graph approach. Just to talk about a few applications for graph or something like this, you can think about the worst company in the world, Facebook, for example, and you have the connection between the users you can be described as a graph. In this case, the graph is not physical. You can think about something that is just as a user. In this case, every user will have some kind of a data which will be attributes of that user that you can go ahead and you can try, for example, to segment the users to some extent, and the users are connected between them. So the edges would be, if somebody is a friend of somebody, it will be the connection over here. Physical graphs are a little bit more obvious because they're visual, so you can think about meshing something, and then you can think about the graph that comes on this mesh. And similarly, you can think about, for example, recently in molecular biology, proteins have been extensively, and chemistry, by the way, generally have been extensively used in graph neural networks, where you're looking at particular, for example, the protein, and you ask yourself which amino acid on which place is close to another one, and you generate this contact maps, which you can think about it as the adjacency matrix in terms of graph. You'll say that, for example, if amino acid number 20 is linked to amino acid number, I don't know, what is it, like here at 90 or something, then you'd have some contact over here. So that's another application for this. So graphs can be, again, very, very useful. And the more you look at these kind of things, you can think that almost anything in the world can be described in terms of graphs, because we almost always, at least in computational science, think about neighbors. We think about whatever happens in one place and something about something else. And that's why, if you're a mathematician, you think about smoothness. Smoothness implies some kind of neighboring. And that's where, of course, graph comes. Let's talk for a second on machine learning on graphs. So machine learning is in a nutshell, in a one-line thing, is when you have input data, which says is X, you have output data, which is called Y in this case, and what you want to find is a connection between X and Y through trainable or parameters you can choose, and the model you're using is F, can be anything in principle. Now we're talking today about deep neural networks, but of course in machine learning it can be a lot of other things that you can think about. Now, when you talk about these kind of graphs, what kind of problems typically you have? Well, I mean, you can have many different things. For example, you can say that you have node input. So you say, here is my nodes, and they're connected in a certain way. And you want to classify the whole graph. So for example, this happens when you take radar data, and the radar collects points. And now you get the distribution of points in space, and you say, that distribution of space represents a cat. So you're going to try to look at all the points together and come with one class for that, or many classes for this thing, but you're not classifying every point on the graph. Okay, that's one approach. The other one is that you want to segment the graph, or find an attribute to nodes on the graph. So this is the picture, for example, over here. When the graphs come unlabeled, I mean, you may have data on every node, but what you want to do is you want to know the color, if you want to think about it, of every node. So you can, for example, say that these ones are blue and these ones are green and the other ones are yellow. Or you can think about it as if this is a social network, that these guys are Donald Trump supporters and these guys are not. So we're trying to find out, based on the links on the graphs and the attributes of the graphs, what are going to be the label of each node of the graph. So that's another approach. And sometimes you're actually interested in the edge information. I'm not going to talk about problems like this today, but it's not really that different. And the mechanism we're going to talk about over here will completely allow us to do these kind of things. So this is, in some cases, would be example chemistry. You can say, well, if I know what the graphs are, I need to know what the links are, or if I want to know what type of connection do I have between different nodes, because not all connections may be the same. So I can talk about edge length, I can talk about type of connection, I can talk about data that resides on the edges of the graph. And that's the other option that that exists out there. So these are the type of problems we're going to be solving on this particular thing. And yeah, we can start going with the machine learning over graphs here. So given the graph, now we cover the second part a little bit. And the second part is the neural network parts. So we said before here, so go back one, so there is this F, which is any machine learning model will have an F here and a theta. So now we're going to cover the F a little bit. So again, a really quick introduction to neural networks, which I'm sure everybody here knows about it. You can actually write a neural network as a recurrent things when you just look at its recursions, that the yj plus 1 is equal to some function, and that function may be somewhat we call activation of some matrix K that multiplies the previous state and maybe some extra trainable parameters. The kernel, this is going to be, we're going to try to estimate it later on. Initially, we think about it as a dense matrix. And I always hated this kind of pictures because, this lines, if you think the squiggly lines here represents just a matrix here. And of course, that's the input layer and the output layer. So this will be yj plus 1, yj plus 2, and so on. And the squiggly lines here, you see they're all connected to each other, means that this is a dense matrix because everything is connected to everything, or they call it sometimes a fully connected layer. Okay? So that's like one approach to do this. In 2000, I believe it was now 16, if I remember correctly, architectures came around to be much more streamlined in some way by using, they call it residual network or ResNet, which is now, again, very well known, very well used, where rather than just having a function like this, they looked at this with yj plus 1 is yj plus all these kind of neural network functions or all these activation functions. We added an H here for obvious reasons, for those of you who know what forward Euler here, because that means that you can take the yj to the other side, divide by H, now take and say that this is really looks like an ODE of this form. So I'm going to move back and forth between the ODE form, this one, to this one. So the ODE approach, again, have been published in 2000, I think, 18, and then 19, and then 20. So there is plenty of papers that discuss this approach as a neural network. The people in Toronto coined it as a ODENet or something like that. But the idea is that it's really a presentation of the ResNet ideas. So again, you can think about this is your model. You have data, you want to predict the data, and now you have to work with that particular model. Okay, and that's going to determine the network architecture for you. So here's an example for this thing, where what you're doing is you're trying to classify things, and you can think about the dynamics. So you can think each time step here is really a layer. And let me just go show it again. What happened here is that you start with the data at a certain form, and the goal is to separate the points. And you give it many layers. And at the end, maybe I should do it and I stop it at the moment, so because I need it to stop some point. And at the end, the bitter end, or almost the bitter end, what you have is you have that the data is actually separated into groups because you define a loss function that wants to separate the data with a linear, with lines, basically. So the neural network, what it does, if you think about it, every layer is giving you a dynamics. But you start with your initial data, and as you progress, the dynamics, the points move in space to the point that they are obeying your loss function, the loss function that you introduced, which in this case was just trying to make things separable as much as possible. So that's that's what happens over here, and that's the way to think about. I mean, that's the way I try to think about neural networks, and that's the way we will think about them here, because we will need the dynamics. We will need to understand what neural networks is doing to the data that we have also on graphs. So this is no graph, this is data is unstructured, everything is connected to everything. But again, when we are going to look right now on data on graphs, we will have to start thinking about what happens there. Okay. Oops, next one. Okay. So before I go to graphs.
Sorry, I just had a quick question.
Sure.
So you think of the neural network input output as an ODE, and then what you're showing is the result of stochastic gradient descent.
No, I'm not showing the stochastic gradient descent. I'm showing what happens through the network. So maybe that should go back.
Oh, I see. Okay.
I should go back. So let's go back to here.
So this is, you fix the network. And
so this, I trained the network already. The network is trained. So the Ks are already set. So the Ks are trained because I did some work before I show you that movie. And now I'm looking at the Ys. I'm just looking at the Ys. This SGD was done. Optimization was already done. We already optimized everything. So now I'm showing you how the Ys behave for the particular choice of Ks that I have over there. And that is actually important to understand because I will show a bunch of those in the next few slides as well.
And the time here, this is, what is it evolving between what? Between the data?
It's evolving between the input layer. So you put stuff in the beginning.
Yes.
So think about it. This is what I put in, right? I put this stuff in. This is the data in. That's the input layer, and the last one is the output layer. So I'm starting with this. I'm ending with whatever happens at the end, right? And as I'm going along, I'm plotting what happened to every layer. So layer one, layer two.
And the limit, you really get a continuum of layers.
Exactly.
Okay. Got it. Thanks. I'm not familiar with this representation.
No, it's worthwhile thinking about it because you can do a bunch of things when you have this kind of interpretation. Embedding something in a continuous process is not necessarily complete. I mean, this is, we can debate it later on, but it's not necessarily completely right, because we are, at the end of the day, with a discrete process, and h does never go to, we always say let h goes to 0, but h never goes to 0. So how useful is that interpretation is always a reasonable question, but that's why I think in the title of the talk, I'm careful enough to say motivated by. It's not a PDE, it's motivated by PDEs or ODEs in this case. Okay. So let's go, we talked about this regular neural network. Before we go to graph, we actually want to cover another case, which is a case of, in some way it is a graph, but we don't think about it as a graph. And that's what people call convolution neural networks. So again, lots of attention people have been giving to convolution neural networks. Actually, the same process exactly as we had before. Nothing has changed really. The only thing that have changed is that before our matrix, remember, was dense. So everything was, the matrix K we have was connecting everything to everything. In images, what you're doing is you're not connecting every pixel to every pixel. It's not economical, and maybe also not as good, it's not generalized that well, because again, an image of 256 by 256 implies you have a matrix of over 50,000 by 50,000 or something like this. And that's of course way too dense and way too difficult to work with. However, if you assume a few assumptions, for example, that things are invariant, then you can work with the same convolution kernel. So you're defining things convolution kernel and work with them everywhere around. And when I talk to students, they tend to confuse the convolution kernel with the convolution matrix itself. What we really have to think about it, that the matrix before that was dense is now sparse. So this is my sparse matrix. I didn't really have boundary conditions here. Basically what it does, it just takes only a few of the pixels that interact with each other. So rather than having a dense matrix that interacts everything with everything, now you're saying my matrix only interacts close enough nodes. And now you can start thinking about what the connection between these two are graph, and I'll talk about this in a second. You can think about that, for example, the pixel over here is linked to all these ones. So if you think about this is nodes, the nodes will be here, and the edges will be connecting between them. It's a special case of a graph, where everything is structured, everything within the same distance, everything is in the same way, and allows you to do a lot of different nice things that can be done with this. And this is where the nice thing that you can start doing this. But you can do the same structure and ask yourself, when I do this, what really happens? So what dynamics can I generate, for example? So I'll just show you 3 examples. So for example, let's say I pick my K as completely random, and I don't do anything with them. So you can take this picture and you can start seeing that it develops some patterns to some extent. You can actually make something, you can choose your K in a semi-smart way, and it can start actually moving things around if you really want to. So you can have a choice to do this, or you can, for example, have a K that will actually diffuse things around. And so these different things happen when you're choosing different convolution kernels in the whole thing. And how did I know how to choose these convolution kernels? It's not that I'm that smart. The only thing I did is I took a course in numerical PDEs when I was a student, and I still remember something about this because I teach it. So one of the things you can do is to think about this thing as really a PDE rather than an ODE. Wait a minute, now we're going here. So if this
can I ask you a quick question, Eldad?
Sure.
I didn't want to interrupt you before, but there are actually several questions in the chat for you. So Christian is asking if there's any hypothesis on the function f in the formulation that you had to guarantee convergence.
So the question is convergence of what? The word convergence is always a problematic. Convergence to a continuous solution, convergence to what kind of convergence we're talking about?
Would you like to specify, Christian? Either unmute yourself or in the chat. Also, I can move on to the next question in the meantime and we jump back.
Okay. By the way, we're using simple f, so either ReLU functions or tan h, so the standard thing, nothing else beyond that. So again, the word convergence is in math is a very tricky one, because if we're talking about convergence of SGT, convergence of the continuous problem to a discrete problem, convergence of a discrete process to just to 0 as something goes by itself. So convergence is always what are we converging to? I
agree. There's many interpretations. So if you would like to specify, just write in the chat, and then Eldad can respond. Another question is, how much would the YJs change if you took fewer steps instead?
So it's actually a really good question because we are trying these kind of things. So don't forget that this whole thing falls into an optimization problem later on. Maybe I'll go back to one. Can I go back like this? Still not good in this thing here. Let's go back here. So think what happened in the optimization process. In the optimization process, we don't know what K is. Okay, we really have no clue what K is. So we're trying to find K such that it will fit the data. Now, if F was not existing, so if everything was linear, for example, or if it's just does not exist in this case, then really K does not matter at all. It's H times K that matters, right? So H is absorbed into the K. So it's because that you have this function here, which again can be ReLU, which is almost linear in this case, again in one part, and then the zero in the other part. Then this H can actually play a role. What you see, of course, is that you see bigger if you have to fit the data, because that's what your loss function really is telling you to do. Then what happens is that you can take H very small, but of course K will start to become bigger as a result. And these are the type of things that you'll have interplay between H and K. So typically what you see is that when you have more H's, more layers, then the interpretation of going towards the continuum makes more sense. Again, if you have only 2 layers, then looking at, I don't know anybody who solves ODEs by 2 steps, or 2 time steps. When you start looking at longer integration times, or basically more time steps, 32, 64, even 18 in some cases, then I would say the interpretation makes sense. If not, the continuous interpretation really breaks completely. Okay. More questions?
Thanks. Yeah, I think there's one last question. Maybe Young Chao would like to specify themselves. It says maybe stochastic matrix representation when, for example, dropout is introduced. I'm not sure what exactly the question was.
Not introducing drop. You can introduce dropout in the training. We're not introducing dropout in the training. You can show that in the training dropout have the same type of effect, of course, as regularization. I'm actually not using dropout. The results I'm going to show you today are with no dropout. Okay, that's a different topic.
Excellent, thank you. That's all the questions for now. Yeah.
I also have a question.
Oh, go ahead.
So if I understood you correctly, you said that the convolutional kernel in this case is also a graph.
Is also what?
So you can consider the convolutional kernel to be a graph, is what you said, I think.
No. The convolution kernel is not a graph. The convolution kernel are the weights on the graph. The image is the graph.
Okay, so you're considering the image as the graph.
Yes, the image is a graph.
Okay.
I claim that the image is a graph. The convolution are just the weights that we apply to the image on the graph.
Okay, fine. Thank you.
Okay. So again, so these movies, we can go on and now. So the question is, how can I do these kind of things? How can I move things around and diffuse things around and everything else? So it's actually relatively straightforward if you just remember that when you're looking at 3x3 stencils, which is what convolution here is all about, you can actually decompose it. You can say that it's uniquely decomposed by different weights. So for example, I can decompose it to 9 weights, where let's take the first one of them, I'll put here. It looks like a -4, 1, 1, 1, 1. And for those of you who remember, this thing is basically the Laplacian, the discrete Laplacian. The other one here, 4, 1, 1, 1, that's like a discrete, with these are not weights, but this is a discrete identity matrix. For example, this one will be a derivative in x, y directions. So you can start expanding any kernel like this into a combination of derivatives. And because it's a combination of derivatives, you can basically do everything that you can do in numerical PDEs with these kind of kernels. Well, not everything maybe, because you're not looking at all the models are slightly different, but you can think about convolutional neural network as just a combination of differential operators applied to the image. And of course, if you now pick the right differential operators, because you know something about numerical PDEs, you can go ahead and you can do advection diffusion or something else. And these things are useful because, just to remind you, and I'll come back to this point again a number of times in this talk, there have been lots of work on PDE-based image processing. And I would claim that what we're seeing here is nothing but extension of the PDE-based image processing that we have seen years ago. So of course it's new, but it's an extension. It's not that convolutional neural networks is something that we have completely not seen. They should be really looked at in that context. Okay. Let go to the next slide. So again, you can think about the image as a graph where it's a regular graph, or for example, if I did not link the corners, then each one is linked to its neighbors, and the weights for the convolutions are really the matrices that we're going to pick and they're the trainable parameters here. Okay, and they usually, and you can just do a simple one because it's always the same edge length, it's always the same structure, always the same number of neighbors, everything is always the same, and that's why convolutional neural network is a simple case of a graph. What happens when you want to go to a more complicated graph? So for example, look at geometrical graph like this. Then of course I cannot really apply convolution. I mean, in this case, things are a different direction. Maybe not all the nodes have the same number of neighbors. You can't go ahead, but you want to still generalize the idea. So what we're going to do right now is talk about how you generalize the same idea of convolutional neural networks, slightly different, into graphs. Okay. So for that, what I need really is two matrices. That's all I need, and I'm going to work with only these two matrices, combining them and playing with them. So I have my graph, and I'm going to have the incidence matrix, or the gradient matrix as we call it, because it kind of looks like a gradient, where all it does, it puts a 1 and a -1 between each nodes. So if you think about this matrix, and by the way, it doesn't matter which one is the 1 and -1, because we will never be working with it as is. We'll always be working with something transpose this. So you can think about putting a 1 and a -1. In many cases, we put weights, which can depend on the edge length. But for the simplicity right now, I'll talk about 1 and -1. This G matrix goes from the nodes to the edges. So again, I have the nodes. You can think about 1 -1 goes to the edge in between. The same thing, I have average matrix, again, without the half here, but it doesn't matter. We sometimes put the half, or it can put any other weights. And what it does, it average every two nodes to the edge in between. These are the two matrices that I need. You can show this is classical graph theory, that if you take G transpose G, maybe with weights, maybe without, that's the graph Laplacian. That will become handy in a second. But that's really the two matrices we are doing. And with those, we're going to build all the graph operations that we need. Okay. So let's talk first of all what other people have done. They have not done it in the way, they've not built it in the way I'm building it right now. But I think it's useful to look at how you build this. So again, if I go back for a second, these matrices do not offer me right now anything that I can train, no trainable parameters. So, and even if I decide to put a W here, it's not really workable, because that means that there is a different, maybe a different W for every edge. That's maybe a problem. So the way to build this thing is to think about a bunch of different operations. The first thing is that at every node, we have a vector of features. So again, if you think about this graph as a graph of social media, each one of them each node will have a vector that represents the user on that particular thing. If the graph is molecular of a molecule, then each of one will have the atom and will have features of the atom, molecular weights, number of for the free charge, whatever you want to put on you have over here. So these one have features. So one thing you can do is you can, what we call 1D convolution. You're just going to multiply every node here with a dense matrix. You can do that easily. Okay. Then you can average the nodes, or you can difference the nodes, and then you have to put it all together. So I'm going to now become a little bit more mathematical. Let's think about all our graph data organized like this. This is U1 to UN, that's every node that I have. And on each one of them, I put the feature vector lying down. So this is going to be U1, U2, so on up until UN. I can think about the 1D convolution as a block diagonal matrix, where I just put the same matrix on the blocks. Of course, I'm never generating it, but that's kind of the way to think about this. And then I have my averaging and my gradient. Okay. Now, how do I put it all together? I multiply this matrix U by K from the right. So that basically average or mixes all the features together. So you take all the features and do the usual neural network salad when you're just mixing everything together. And then you're multiplying by the gradient on this side. So you're moving whatever you were here to the edges, and you're moving again this one to the edges by averaging. By the way, you can have two different Ks if you want to. It's perfectly fine. This is just simplicity right now. So that's your first thing. The problem is that right now you're at the edges. And remember, if I want to update, I need to be back at the nodes. So how do you go back to the nodes? Well, you multiply by different matrices, so two different matrices here. One of them I call A hat transpose, the other one G hat transpose. Of course, most of the time, you can pick them as just the transposes of the other ones. And that's how you're going to move back to the edges. Now you can see immediately that when you do this, you get G hat transpose G, A hat transpose A, and these are kind of like going to be like Laplacian matrices and mass matrices, which I'm going to specify in a second. Okay. So this is going to be so far everything here is linear. In neural network, after you mixed everything, you have to put nonlinearity. So here you put nonlinearity on top of this. So this is your activation function, which is going to be either a ReLU or a hyperbolic tangent. And this is your layer. So now you have a layer. And the last thing when you do, you combine everything in the ResNet style. So you say, okay, UI plus 1 is UI plus that layer that depends on all these matrices. And K is the only trainable parameter here. So you really have to look at K as the thing that happens here. Okay, so that's the way people have done this initially with great success to some extent, but had some issues and some things that were not really well explained. And I'm going now to address these things. Okay, so again, this is the standard neural network. If you want to think about it more from a point of view of how information passes, you say, well, first thing I mix, or first thing I take the information. I mean, it doesn't matter; these things are commute. So you say, okay, I can take information from you, move it to the edges. Then I take the information on the edges and mix everything together, and then I update. So that's different things that happen. There are many different. The field is really happening. I think that. There were 70 papers in the last big computer science meeting on these things. So many different variations on these things. I'm not even attempting to try to cover them all. And there are some theoretical results or some known problems, but generally speaking, there are some problems. I mean, there are a bunch of problems that exist, and I'll talk about one of them in particular in a second. And a lot of, it seems like band-aids to fix these problems rather than a systematic way. And this is the main problem that people face with. And there again, the bandwidth, there are some advantages to fix this thing. So the problem is problem of oversmoothing. There is a data set that we'll also explore here. When you start with some kind of a graphical, you basically have some data that is, you put it on the mesh that you generate on in this case on a person, and you try to run your neural network forward. And what you see is, as you're running it, but the whole thing is becoming more and more uniform in color. So it's much more difficult to generate, let's say, things that will distinguish between different parts of the body in here. And if your data requires this, that becomes very difficult to fit the data. So this is called oversmoothing, that people have noticed this phenomena. And this is why GCNs have typically been very shallow. So people were not very happy to put many layers on GCNs. There was claim that this thing maybe does not need many layers, that there is no reason that you can work with this. And the first thing we want to understand why, and can we fix it, and maybe come up with a solution that will allow us to do more than that. So here's the simple explanation. I mean, if you are going to look at the layer and choose, and let's see, I have a typo here, but that's okay. Choose the G transpose to be G, or minus G, I would say, and the A transpose to be just like A. Then what you do is you can get a layer that looks like this, where this is a Laplacian matrix, and this M is like a mass matrix, basically like an identity operator. So if you think about your PDE that you're getting, or what type of PDE I'm getting, this is where you have a ResNet, but think about this, the discretization of a PDE, then the PDE is really a heat equation. So what you have is some kind of nonlinear heat equation, where you think about ut is equal to Laplacian of u with some coefficient k that are mixing the channels. And of course, this is smoothing. So why are we really surprised that this is smoothing? That's exactly what the physics of the problem should tell us. And this is what we should see. When you understand that, you say to yourself, okay, I mean, if that's smoothing, I can build mechanisms to A, control the smoothing, and B may have things that are not smoothing it altogether. And that's what I'm going to show you right now in the next few minutes. So I'm going to now construct the whole thing again, but I'm going to construct it a little bit different. So the same mechanism, the same U, the same Ks, the same As, the same Gs, but I'm going to combine them in a different way. The motivation is really coming from finite volume, PDEs that are made from finite volume. And really, if you remember these kind of things, finite volume a little bit, then you remember that you start with actually an energy, or the one way to do it is to start with an energy. And the energy is basically the gradient of the field you're looking at, the scalar field, the potential field you're looking at, square, multiply by, let's say, the diffusivity. And when you take this thing and you differentiate it, you get the famous Poisson equation out of this whole thing. So you can write as a Poisson equation, this is equal to 0, you're looking for steady state. If you're not looking for steady state, you're looking for some kind of a diffusion process, then you start with a certain u, you start at some point and you just march forward, and that generates basically the general heat equation. And now you can look at this and say, can I do the same with my neural network? And the answer is definitely yes. So this is the energy that we have here, and I'm going to define an energy in a similar way. I'm going to define neural energy, and we're going to use a sigma I. So rather than sigma hyperbolic tang over here, I'm using something which is the integral of sigma for the energy. And the integral of hyperbolic tang is log cosinus hyperbolic, which is basically looks like an absolute value function with a smooth bottom here. So if you differentiate this, you get back the heat equation. If you differentiate, that, you get exactly a layer that is very similar to what we had before, but slightly different. So you see before everything was inside the sigma, now the G came out as a transpose outside, this K came out as a transpose outside. Things look a little bit different, but that's the layer you have. And now you can come up with a heat equation that is really obeying some kind of a variational principle over here. By the way, this is for constant K, so I'm a little bit cheating here. You can we can talk about this if you want later, but for constant K, for sure, this is basically a nonlinear heat equation that reduces this energy because it's just flowing in the gradient direction for this particular thing. So very similar to a finite volume discretization of on PDEs. Now, why do I like these things? Because, well, again, as I said before, you can think about this whole thing as a very similar idea as to what people have done in image processing for many, many years. Where if you look at all these PDE-based image processing, Perron-Amelli, anisotropic diffusion, total variation, denoising, you can think about all these things. They're all based on the same idea. What you do is you take the gradient of the image, which you in this case is the image, you move it to the edges of the image or the edges between pixels. You do some nonlinear operation on that thing. So in this case, our nonlinear operation is this sigma I and K, and then you sum it all, generate an integral, and the derivatives is giving you all these different methods. So if you think about what we're doing right now is really not that different than what people have been doing for years, starting in the 90s or maybe the 80s even, on PDE-based image processing. The only difference, and it's a big difference, is that it allows us to choose energy that is based on empirical data. We're not going ahead like Mumford Shah, for example, and say, here is our energy. And we thought about this long and hard, and this is how we get the energy. Today, we try to not think about anything too long and hard, and we just go ahead and say, let's the data do this. So all we do is we're building a machinery such that we can take the data and it will pick the function for us, rather than we are going to give the function away by choosing something. But the mechanism is basically identical. So that's kind of the nice thing about thinking about energy. Okay. So to summarize what we're doing in terms of the layer, let me kind of do a visual thing. So let's kind of think about this thing as starting over here. At every node, I have a vector. So this is, for example, ui and uj, and I have an edge in between them. What I do is I generate the sum of the features and the subtraction of the features between each one of them. I multiply by a matrix K. I add a nonlinearity. I multiply by the transpose of that matrix, and then the information flows back by the transpose of the gradient and the transpose of the averaging matrix back from the edges back to the nodes, and then I can add it together. So that's basically the graph layers that we're using. So again, so we said before that the diffusion can be a problem, and again, some problems. So again, one of the things that I'm working on for now a few years is looking at the neural networks as thinking about more as PDEs or ODs. You say, look, I mean, when we're doing Navier-Stokes equation, we have one type of PDE. When we have something else, we have a different type of PDEs. Not all PDEs are good for all problems. So in some way, not all neural networks should be the same architecture for all problems. Some problems may require diffusion, and that's great. So for example, you can think about image classification or points classification as something that you don't mind smoothing things as long as it's smooth to the right value. Who cares what the value at every node is if eventually you're averaging everything to get like one number. On the other hand, if you want to have things that are varying on every node, you may not want to smooth things too much. So now you can say, well, I mean, who says that this thing has to be with the first derivative? I can add the second derivative over here. Machine learning, that's kind of the nice thing about it. If you don't like the PDE, replace it. Okay? So you can come up with this model, which is a slightly different model. You can come up with a model that have a wave plus a diffusion term where they're balanced between each other. So I'm going to talk a little bit about these two models or use these two models, but these are standard things. You can discretize this by leapfrog method. This is, again, a combination of leapfrog and forward Euler if you want to, and go ahead and just use these things in order to try to solve your problem. Go to the next one. Okay. So again, I mean, the ones that we're actually looking at are these three models. And what we will see in a second is that either we choose the model, or sometimes we say, let's try to even learn what the model is. So we're going to, for example, say this alpha can be a trainable parameter, when I can say, you know what, let the system decide, if I'm not sure what the thing would be, what the right thing for this to be. Okay. So with that, I'm going to go to numerical experiments. We actually played with a number of data sets that are out there from the Stanford collection of data sets on these things. They're not huge problems. That's kind of the nice thing about it. I think the biggest one was the protein-protein interaction here, but which takes a little bit longer time. And the nice thing is that they allow you to test these methods relatively quickly. So you can run things and see how it works and see what happens. So we looked at this thing and we said, okay, let's try ours and compare to other methods. One of the things that that happened first is that you realize is that when you're looking at different methods, we're looking at methods that people are using, they can be very finicky. So for example, you're using a data set called Cora, which is a very easy one, and one which is ModelNet 10, whatever that thing is. And you're using standard what's called GCN. So you're looking at these kind of things, and you see that when you're using this on one data set, the accuracy is 92.8, and then you're changing this, and you're just changing the data set. Nothing, like you say to yourself, it shouldn't be that different. The accuracy goes, down dramatically. There are different variations. I told you, the papers appear on these things every day almost now. So there are different variations, things improve a little bit, but the fact that you have such a success on one and such a failure on the other is really saying something. When we use ours in our case, again, the results are kind of not, both of them are in the state of the art, more or less results. They're not changing dramatically. Okay. So going in the spirit of the Olympics, the word that everybody in the Olympics should know right now, and you learned it in machine learning very quickly, for those of you who are not, is called SOTA, state of the art. The first thing that they should ask any Olympian, are you doing SOTA or not? And the first thing to say is that this technique is the state of the art. So if you're looking at all these different problems and you compare it to all these different methods, and if you ask me, do you compare to all the methods? The answer is definitely not. Again, there exist many of those, but these are the major ones in the literature. We're either the state of the art or very close to the state of the art. So, and this has been to almost any problem we tried on when the data set is given and you just want to see how well you're doing. Very quickly, you can get to something which is close to the state of the art. So it's not just a nice mathematical technique that they can talk theory about, but actually it's one of these places. And to be honest, being in the neighborhood for a long time, in many cases we come up with really mathematical theories that when you take them to practice, they don't work that well. This is one of these cases that it's nice because you take the math, you apply it, and it actually works. So that's kind of the nice thing about it. The second thing is you can see that oversmoothing is control. Again, there are a lot of other methods that try to do these things by doing things that are not fully understood, more tricks. In our case, you go, 2, 4, 8, 16, 32, 64, no problem. And again, this data set is not necessarily, and it requires, as you can see, so many layers, and you're not really improving that much. But again, no problem of oversmoothing. You can just add layers if you wish, if your problem requires this, and that should be fine. The other thing is that it's important to understand the right dynamics. So we actually tried a data set that we like, that in this data set, smoothness is actually not necessarily is that if you over smooth things can become really bad because you have interfaces that can be quite bad. So if you don't choose the right dynamics on this thing, you can actually have something that is, like, this is our method here, is not standard, right? And if you choose the right dynamics here, hyperbolic, the H stands for hyperbolic, so we actually use something that does not decay things, we're getting basically better than everyone else on this particular data set. So it is important to think what the right dynamics you have for your problem. Okay. The next thing is that you can actually learn the dynamics. So we tried for both of these problems, the one I showed you before, and another one, which is a social network problem, to say, okay, let's add alpha to the mix and to the salad of training things. And can it learn this thing? And it was actually nice because you can see that the thing here basically learned that alpha should be 1. So it's basically it goes to the wave type equation. So it goes to the hyperbolic type equation. It says, I want to have something that you can control better the smoothness. And in the other one, it says, no, I don't need something that will do this, and just everything went down. The alpha went down as we iterated. And basically, we're solving an equation that we really have. This term is its major thing, and the wave term almost does not exist. So you can actually learn the dynamics if you wish so by just adding this whole thing to the parameters. I would argue that this adds complexity. That if you know what the solution should be, you should not add this thing. But again, this can be done. The other one that was a little bit surprising, to be honest, was, and this is where I say the theory justifies something, is that energy is important. Why do I mean energy? Remember that for the whole K transpose here came from the fact that we minimized a layer. We came with an energy, we say we're going to go in the direction that minimizes that layer, and this is why the K transpose came here. So now you can say, you know what? Who needs this K transpose? I'm going to use what most people in this industry do, and they use a K1 here and a K2 here. So it doesn't have to be a K transpose. When you do that, you're getting a little bit less. The results are not as good. They're close, but they're not as good. So the non-symmetric version is going to be not as good as the symmetric version, and was kind of surprising because I thought in the beginning that it's nice theory, but in practice we're not going to see any difference. Or maybe even the non-symmetric one will give us better results because it has more degrees of freedom. This does not happen for these kind of experiments. Again, because we're looking at data science, there may be a data set that this would not work, but at least for the small number of experiments we have done with this, it shows that the energy, the derivation from the energy seems to be nice and actually justifying its existence in somehow. Okay, so that was another one. Okay, so before I kind of finish here, we have the following things. So first thing, I would say that we just developed extended graph DNN beyond images. So that's what really graphs neural network, you can think about them. There are many possible uses when you start thinking about using graphs for different problems that you have. Almost any data you can think about, you can describe as a graph. The question is, do you want to do it? But these suggest that you can, and then you can do something with this. We propose a variational approach for these things. And it generalizes the way I see it, at least PDE-based image processing and other variational approach. We managed to get really good results on a lot of data sets here and show that these things actually make sense to look at this. I promise no references, but at the end I'll give you just one. There are some references. The paper on this will actually come out, I guess, in what are we right now? We're 20. So I guess in less than 10 days, maybe a week or so, there'll be a paper out with all the references and everything else. But this is all I have to tell you for today, in a sense.